differential equation, dy dt equals 3t to the second. So the first step would be to separate the dy and dt. So it kind of looks like multiplying both sides by dt, and you can think of it that way, just don't say that that's what you're doing. So we'll bring the dt to the other side of the equal sign. So we have 3t squared dt. And then when you're solving differential equations, you integrate both sides of the equal sign. So we'll integrate both sides, and so then that becomes the integral of dy equals the integral of 3t squared dt. So now you use your power rule. So the integral of dy, so that would be a 1. So the antiderivative would be 1y, or just y, equals, and then for your 3t squared, that would be 3t, and then 2 plus 1, which would be to the third power, over that third power plus c. And so your solution is y equals t to the third plus c. And this is what we call the general solution of that differential equation. So there's your first example. Your second example will be working on solving the differential equation f of x equals negative 12x to the third plus 10x, and we're given that f of 3 equals 2. So finding a particular solution. So since this is not written in dy dx form, we're going to just start by integrating both sides of the equation. So I'm going to start us off with f prime of x as it's written. And then you might put a little space after your equal sign, equals negative 12x to the third plus 10x. And so we will integrate both sides. Now, when you integrate and you have a f prime of x, then you need to put a dx with that. And then when we integrate this other side, so we'll integrate the other side, again, you need a dx with that. And so the antiderivative of f prime of x is the original function, f of x equals, and then we'll do our power rule. So that would be negative 12x. Now it's 3 plus 1, so 4 is your exponent. And we're dividing by 4. And then we'll integrate the next term with the power rule. So 10, and then x, we'll add 1 to the exponent, so that will be squared. We'll divide by that 2. And then remember, plus c. And simplify. So f of x would be negative 3, x to the fourth, plus 5, x to the second, plus c. And then now you'll find c using your given information. So we were given that f of 3 is equal to 2. So this was given, that f of 3 is equal to 2. So think of that as the ordered pair 3, 2. So you have an x and a y value. And you can substitute that in, so into your general solution. So 2 equals negative 3, and then x, which would be 3 to the fourth, and Then we'll add to that 5, and we'll put in 3 again. And that's to the second power, and then plus c. So c is what we're trying to find. And then you'll simplify that. So we'll get 2 equals, and if you do the math on all of that, you'll get negative 198 plus c, and then bringing the 198 to the other side, 200 equals c. And then the next thing, and I just barely have this blank showing on my screen, but it says rewrite the general solution by substituting the value of c. So this is our general solution. And so f of x, the particular solution, when f of 3 equals 2, or in other words, the particular graph that intersects the point 3, 2, that has that point on it, would be negative 3x to the fourth plus 5x to the second power, and then plus 200. So out of that family of graphs that we found in our solution, we found the one graph that goes through the ordered pair 3, 2. And so that's what we mean by finding a particular solution. So if you'll turn to the back of your notes, we'll look at some other types of solutions that you'll be asked to find. So for your third example, it says to solve the differential equation where you're given f double prime of x equals 2, and then given information that f prime of 0 equals 6, and that f of 0 equals 3. So this we're going to have to go through twice, noting that the antiderivative of the second derivative would be the first derivative. So if we start with our original information that f double prime of x is equal to 2, and then we integrate on both sides. So when you write your integral sign, be sure that you put a dx. We want to integrate on both sides of the equal sign. Then the antiderivative of f double prime would be f prime of x. And I didn't say it on the front, but when we're doing this solution of differential equations, we only add c to the side that is not the function name. So in this case, we have the antiderivative of 2, which would be 2x, and then plus c. So now you're going to use your given information. You are given that f prime of 0 is equal to 6. And this is the information we have to use at this time because f prime is the function that we're working with. So we have the ordered pair 0, 6. And so we'll put in 6 for the y value equals 2 times 0 plus c. So I'm using this f prime of x equals 2x plus c, plugging in the 0, 6, and that gives us a c value of 6. So our solution for f prime of x that has the ordered pair of 0, 6 is f prime of x equals 2x plus 6. And then we're going to keep going because I want to know the original function. So we'll integrate both sides of the equal sign again. And the antiderivative of f prime of x would be f of x. And then we'll need to use our power rule. So for 2x, we'll have 2, and we'll add 1 to the exponent and then divide by that. So 2x squared over 2 plus, and then for the 6, it would be 6x plus c. So simplifying, f of x would equal x squared plus 6x plus c. Then we go back and we look at our given information again. This time we were given that f of 0 is equal to 3. We'll substitute that into our general solution. So 0, and this again is the ordered pair 0, 3. So 3 will go in for the y value, 0 in for the x's. So we'll have 0 squared plus 6 times 0 plus c, and that will give us a 3 for our c value. And so our solution to this differential equation with the given information that we want our final graph to go through the ordered pair 0, 3, or to have that y-intercept would be f of x equals x squared plus 6x plus 3. So this is what you'll be asked to do anytime you're asked to solve a differential equation. You will integrate both sides, and then if you're given information, you'll go from the general solution with a plus c to a specific solution where you will calculate the value for c. So we'll continue on and look at an application involving motion. This will be our next problem. So on number 4 of your examples, it says on the moon, the acceleration due to gravity is negative 1.6 meters per second per second. So notice that this is acceleration. A stone is dropped from the cliff on the moon and hits the surface of the moon 20 seconds later. Write a function to represent the position of the stone. So we want to go from acceleration to position. Well, so we'll start with what we know, and that is that our acceleration, a of t, is equal to negative 1.6. And the antiderivative of acceleration is velocity. So we will integrate both sides of that equation. So the antiderivative of a of t dt would be equal to the antiderivative of negative 1.6 dt. So I'm just integrating both sides of that acceleration function. And again, the antiderivative is going to be v of t. It's going to be the velocity. And then doing our antiderivative, we would have negative 1.6 t plus c. Now, you're given information. It says that the stone is dropped, and it's dropped from the cliff from a cliff that's on the moon. And so we want to think about where we are with this. If something is dropped, and we're looking at velocity, so if it was dropped, that means that at time 0, so at time 0, the speed or the velocity was a 0. So at time 0, the velocity was a 0. So we have the ordered pair of 0, 0 to plug in. So we would plug in and have 0 equals negative 1.6 times 0 plus c. So 0 is our c value, and so therefore our velocity function is just v of t equals negative 1.6 t. Since our c was a 0, we don't need to write that. So now we're supposed to be going to position, so we will integrate both sides of our equal sign. So the antiderivative of v of t dt and the antiderivative of negative 1.6 t dt. And as stated right in this line, the antiderivative of v of t is s of t, or position. So s of t is equal to, and then we'll do our power rule. So negative 1.6, and then it's t. We'll add 1 to the exponent, so t squared over 2, and then plus c. And so simplifying that, we would get s of t is equal to negative 0.8 t squared plus c. And now we'll go back and look at our given information. So for the given information, it says it was the stone was dropped from a cliff on the moon, and it hit the surface of the moon 20 seconds later. So at time 20 seconds, so the time is 20, and the position is that it hit the surface of the moon, and that would be ground zero for the moon. So the position would be at 0. So you have the ordered pair of time versus position at 20, 0. And so that's what we can substitute in. So your 20 is your time, your position is the 0. We'll substitute that in. 0 equals negative 0.8 times 20 squared plus c. And solving that, you get that c equals 320. And so the position function is s of t equals negative 0.8 t to the second plus 320. So that's the position function that then we should be able to answer whatever questions are asked. So one question that we need to find out is, how far did the stone fall? Well, since it fell from the cliff, the highest that the stone would have been would have happened at time 0. So at time 0, the stone was its highest position that it would have been. So that means that if we could plug in 0 for the time into the position, we would be able to find that out. So negative 0.8, put 0 in for the time squared, and then plus 320. And so that would give us 320 for the position. S of 0 would equal 320, and that would be in meters. So the stone fell 320 meters. And then another question that we might be asked is, what is its velocity at impact? Well, the time was 20 seconds when the stone fell to the surface. So now this is asking for velocity. So what is its velocity at time 20 seconds? In other words, V of 20. So we would have negative 1.6. You want to be sure you're using your velocity function, negative 1.6 times 20. And so V of 20 would equal negative 32, and that unit would be meters per second. So negative 32, negative because the stone is dropped. And so the velocity at impact is negative 32 meters per second. Okay, so we have that as your application of a motion type of problem. And then I'm going to do a separate video for the last two examples, which are involving some graphs that I'd like to discuss. So this will be enough for the application problems.